So one thing that I think's been really overlooked by weather people is tropical nights. This is not a party in Benidorm. We're talking about an event which is characterized by the temperature remaining above 20 degrees for a 24-hour period. And it's quite important to realize this. You know, if you get down to 12 degrees at night, then the building that you're in can lose a great deal of heat. But of course, if it stays above 20 degrees, you're not going to lose that heat. And if you're in a building that overheats, then you can't get that building cool. So you're living in a flat, um, and it may not get below 25 degrees for several days. This is a really serious issue. In July 2022, when we had this big heat wave, the UK experienced 3 consecutive tropical nights. This is a significant milestone in the country's climate history. It was very severe. We had a lot of very hot weather in that time, but it did get reported, but I don't think people realise the impact it has. And here we have Leeds, well, it's not Leeds, this is Sheffield, Nottingham, and Wakefield, and they had the 3 tropical nights where it didn't drop below 20 degrees. The UK, by the way, the UK's highest recorded minimum overnight temperature is 26.8 degrees, and that was in Oxfordshire in July 2022. Massive issue if your home's not designed to lose the heat. So refrigeration efficiency. Remember, efficiency and high ambient temperatures are linked. If you don't know, refrigeration efficiency is expressed as the coefficient of performance. That's the COP, or miles per gallon, and the COP is the cooling capacity divided by the absorbed power of the motor. For one degree increase in the condensing temperature or ambient temperature, refrigeration efficiency reduces by 2 to 4%. So when you most need your cooling, it's going to be reduced. The compressor accounts for about 95% of the power used by a refrigeration system, and the condenser fans are 5%ish. So it's the compressor that uses the most amount of energy. The more heat the condenser ejects, the less work the compressor must do. So it's really important that you keep your condenser clean so you can reject the heat, because if you don't, the compressor must work harder. As condensing temperature increases, two things happen. The first thing that happens is the cooling capacity is reduced. So when you most need cooling, your cooling capacity is reduced, and the absorbed power from the compressor increases. What I've done here is I've put this is a Danfoss scroll compressor. It's on 410A, and we're evaporating at 0 degrees there. This is our condensing temperature, cooling capacity, the absorbed power, and then there's our COP, our coefficient performance. So at 30 degrees, cooling capacity 70.71 kilowatts. The absorbed power is 13.55. That's from the compressor. If you divide 70 by 13.55, your COP is 5.22. So for each 1 kilowatt of input power, you get 5.22 kilowatts of cooling. Look, if the condensing temperature increases by 10 degrees to 40, the cooling capacity is reduced. The absorbed power has gone up, and our COP has gone from 5.22 to 3.81. So it's 37% reduction for 10 degrees. Remember, I said for each 1 degree increase in condensing temperature, refrigeration efficiency is reduced by 2 to 4%. So poor installation design and maintenance can reduce refrigeration efficiency by 50%. I've talked about this a great deal of time in my webinars, which if you've not seen them, please sign up and see. They're all in the library. And simply we can spend millions of pounds on new equipment, but if it's installed and poorly, the design's poor, the maintenance is poor, it will reduce the refrigerator efficiency by 50%. So it's very, very important that we get these things right, particularly if we're changing systems for something for the future. It must be installed properly and maintained properly. So poor efficiency will reduce the rated cooling capacity, and it may not meet its rated performance. This is critical if ambient temperatures are going to be increased. Designer specification. If you're looking at designing a system, there's a few things that we need to know. We need to know our cooling load. We need to have the cooling capacity of the system. We need to have our space temperature. We need to have our design, our peak ambient temperature. Well, what I'm trying to say now is let's forget about the ambient temperature. Let's talk about the air on temperature, because this is often different to the peak ambient temperature. And we might want to build in some redundancy to the system. So these are the typical design considerations. Other types of considerations are the type of compressor, the type of condenser, the refrigerant, whether it's a DX or a secondary refrigerant, i.e. sending cold glycol around the system, and the efficiency. They'll all be part of the specification, but a well-sized condenser will have a huge impact on efficiency and meeting demand. So remember, the more heat the condenser ejects, the less work the compressors have to do, which improves efficiency. So design and specification, the total amount of heat the condenser has to eject is the sum of the cooling capacity and the absorbed power. And an efficient system will have a well-specified condenser with a low condenser delta T. It's really important to grasp that. The lower the condenser delta T, the more efficient the system is. Understanding condensing temperature. So quite a few things can have a big effect on condensing temperature or the air on temperature. Dirty fouled coils, low speed fans, poorly located equipment, something like the incorrect refrigeration charge or refrigerant charge, and a restriction in the refrigerant line, so sort of block filters, can all affect the condensing temperature, and it will increase the condensing temperature, and of course then it will reduce the rated performance. Just to recap here, so that look here we can see how performance is affected as the air on temperature is increased for a typical screw compressor on R290. So we've got our air on temp here, we've got our condensing temperature, cooling capacity, absorbed power, and our COP. And this is based on a Bitzer compressor. There you go. Now, here you can see air on at 30, condensing at 45. The COP is 3.27. If the air on is increased by 2 degrees, condensing temperature goes up by 2 degrees, and our COP drops 3.09. Air on 35 degrees, and now condensing at 15 degrees. So we've got a 15-degree TD. Here we can see the cooling capacity is dropped, absorbed power has increased, and our COP again is dropped to 2.84. And finally, if the air on temperature gets to 40 degrees, and we've got that 15-degree TD, we'll be condensing at 55. The cooling capacity has dropped to under 88 kilowatts. Absorbed power has gone up, and our COP has dropped to 2.46. So that 10% increase in condensing temperatures these are the facts and figures. It's reduced the refrigeration efficiency by 33%. It's increased the absorbed power, by 14.1%, and it's reduced the cooling capacity by 14.4%. So there you can see that 10-degree increase has had a big impact on the system efficiency.